Okay, in the last video, so we looked at dynamic programming, which was when we had a situation of, um, of recursion, but we had overlapping subproblems. We're going to come back to that later on, but I just want to go back and just look at a classic problem in recursion. Everyone who ever took computer science courses solved this problem. It's really a classic, and it's called Towers of Hanoi. Some of you might have heard about it. Let me just describe it, and then I'm going to show you a website. I'd like you to just go to that website and then play with it a little bit. And what you want to do is you want to try to come up with an algorithm to solve the problem. Okay, we'll talk about why that has to do with recursion and so on, but it's a very interesting problem. And as I said, everyone who's anyone has solved this when they were computer science majors. Well, here's what the problem is. You're starting with 3 towers, right? So let's call this tower here A, and this tower B, and this tower C, right? So the idea is you want to end up moving all of the rings on tower A, say, to tower B. Sometimes it's from tower A to tower C. We're going to do our A to B, but it's the same thing. Doesn't make a difference. So the idea, so what's the problem, right? Just lift the thing up and move it over. So the problem's like this. Just like anything that's really interesting, you have to work within certain boundaries, right? There are certain restrictions. So the restrictions are the following. You can't just lift this whole thing over and bring it over. That doesn't work. That's not what you have to do. What you have to do is you can only take one at a time, right? You can only take one of these rings at a time. So if you take this ring, you can move it either to B or C. So that is rule number 1. Only one ring can be moved at a time. Now, what does a move mean? It means take the ring. You can only move the ring at the top. You can't, for example, say, well, this one looks nice, I'm going to take that one. You can only get the ones on the top. That's the only one that's available to you. And you can move it to one of the other rings, but there's a proviso. And that is you can only move it onto a tower that has a ring, either a tower that's empty, that's okay, or to a tower that has a ring on it that's larger than the one that you want to move. So, for example, if I want to move ring number 1, this guy here, and this ring is here, so I got a very big ring here, then I'm allowed to move this and put it on there, right? So every move consists of taking the upper disk for one of the stacks, that's the only one available, and placing it on a top of another stack or an empty stack. But you can't, no large disk may be placed on top of a small disk. You can only put a smaller one on top of a bigger one, right? So for example, if let's say the smaller one is sitting over here, then you can't bring any of these on there because you only put a smaller one on a larger one and not vice versa, right? So again, one ring at a time. You can only move one that's on top of a stack. You can't stick your hand in the middle of this thing and move it. And you can never put a larger ring on a smaller one. So that's basically the idea. So what I want you to do is there is a website, right? Here is the website. And I found the website by going to mathisfun.com, or just Google Tower of Hanoi Math is Fun. And you can actually try you can try it. So I think here what they want you to do is they want you to go from this tower here, this tower we called A, they want you to go over here. So you press I don't know, how do you do it? Just pick it up, I guess, and you move it over. So I can move there to there, and then I cannot watch what happens if I try to put this here. It doesn't go, right? Because it's a bigger one and a smaller one. But I can put this one here, and where do I put this? Not there. Not here. So you get the idea, right? So what I want to do is I want to restart the whole thing, and I want to solve it. So try to solve it for 3 rings, and once you get it for 3 rings, try to solve it for 4 rings, and if you're adventurous, try to solve it for 5 rings. And what you want to do is you want to figure out an algorithm, right? This is not such an important problem, but it's a very good test bed for you to develop an intuition about algorithms. And as you're doing it, I want you to reflect a little bit and say, why in the world are we doing this now? What does this have to do with recursion, right? See if you can figure this thing out, because this is it's a very neat problem. So I hope you figure this out. Let's see how it works. So I want to get all the rings from this tower we called Tower 1 to Tower 2. When you run the simulation to say solve it, it's going to try to go tower to tower 3, tower C, but let's imagine we go to tower B. So I can do it like this. I can say what? I can say take this one and put this over here. That's one move. It says the minimum number of moves is 7 down here, right? And then I can move this over here. That's 2 moves, and I move this over here. And then I go this way, and then I got to bring this over here, right? So I bring this back. Remember, I can only move one at a time, and always the top ring, and then I'm done. So I've done 7 moves, and I've gone from tower A to tower B. If I want to restart this thing and just watch them solve it, so they're going to go to tower C. That's the way the simulation works. It really doesn't make a difference, you'll see. It's the same basic idea. Let me restart this. So that is the idea. So now what does this have to do with anything? I mean, what does this have to do with recursion? So the basic idea is the following. Let's say 3 rings. I have 100 rings, right? So the rings are going to be 1, 2, 3. This one is the smallest one, all the way down to 100. And what I want to do is I want to bring 100 rings from A to B. Now, let's see what's clear over here, right? So I want to move 100 rings, and they want to end up on B. So if you think a little bit, you realize that somehow the ring marked 100, this one here, has to end up here, right? So the only way that I can get this ring from here to there is to free it up, right? There can't be anything on top of it. So that means we have to do the following thing on a very, very high level. Somehow I've got to get the following thing to happen, right? I'm going to start with all the rings from 1 to 100 on tower A. But the first thing that has to happen is somehow I have 1, 2, 3, all the way up to 99, right? Somehow I got to get these guys over here. I have to end up with 1, 2, 3, up to 99 over here. And the reason that I have to do that is because otherwise I will not be able to move ring 100. Does that make sense? So we saw from the previous thing when you were playing with the website that it didn't make a difference. I'm going from A to, it's the same kind of moves, right? It didn't make a difference going from A to B or A to C. So what you see is in order to move 100 rings, I had 100 rings over here, then there's a sub problem that I have to do, and that is to free this up, I have to move 99 rings from A to C, right? I want to get 100 moves, I want 100 rings from A to B. The first step is get 99. That's step number 1. What's step number 2 going to be? Step number 2 is after I free it up, I'm going to bring ring number 100 over here to tower B. And what's step number 3 going to be? Step number 3 is just to take these things over here, and somehow that's going to be step number 3, get them on top here. So when I end up, I'm not going to have 1 to 99 here, but in fact, I'll have 1, 2, 3, all the way up to 100 over here, right? So it's a 3-step process, right? Step 1, so a 3-step process of what, right? To move 100 rings, first move 99 rings, then move 1 ring, and then move the 99 back, right? So what does this have to do with recursion? Because what's the essence of recursion? Recursion you use in the following way. Recursion, you say, well, I've got to solve some problem, and the problem is there's a parameter here of let's say some n. In this case, the parameter is 100, the number of rings. So if you can say, if you can break the problem up into the following way, you can say, well, I don't know how to move 100 rings. I don't know how to do that. But if I could magically move, if I had a magical subprogram, magical function that could move 99 for me, then I could move 100. So you see, but what's interesting is that it's the same function, right? I mean, it's the same function with a different parameter, right? What I'm saying is, I want a magic function to move 100. I don't know how to do that. But if I have a magic function to move 99, then I could use that to solve for 100. So it's the same function, and I say if I can use that same function with a smaller number, I can then construct the thing, the algorithm for the larger one. Now, also I want to point out that what we're going to do you'll see in a little bit, we're going to actually simulate this thing using the activation records. But it's very important to understand that that's not the way a programmer thinks, right? If you start thinking about activation records, you'll never solve the problem. What you have to do is you have to solve the recursion on a very high level, right? You have to sort of trust in the beginning, and then you build up the intuition. You have to say, well, can I sort of use the same exact algorithm, but for a smaller number, for a smaller value, for a smaller object, to solve the bigger one? And then don't worry, the machine will take care of itself, right? You have to think on that high level, but it's good to see for a couple of times to actually work it out by hand to see how it works, just to get a feel for what's going on in the machine, to convince yourself that it really works, but also to get a feel for the complexity, what's going on, how many steps it might take. Okay, so I can't stress that enough. You have to really, sort of, it's a leap of faith in the beginning that it works, right? What works? If you have a problem that can be broken down to use the same problem, the same function, but on a smaller value to build up the one for the higher value, and then of course you need a base. That is recursion, and it's extremely useful. Okay, so let's see if I can sort of formalize this a little bit, and then we'll see how to do it in the general case. So what if I want to write the pseudocode for the case of these 100, right? So let's say I have a function called move, and what I'm going to do is I'm going to have a from tower. I'm going to move things from tower to a to tower, the one that's extra one, we'll see in a second. I want to move 100, right? That's what I want to do. So in our case, the from tower, where's it coming from? The from tower is tower A, the to tower is tower B, the extra tower is C, and we'll call this thing N. N is the one that we're going to do, right? That's the one we're going to, that's the number of rings we're going to move. So the first thing is going to say, well, whenever I have a recursion, I need a base case. Well, the base case over here is if I only have one, right? So for example, in the case over here, I only had one, right? Once I freed everything up and all I had was 100 over here, I didn't call the recursion again. That would have been a base case. All I do is then I just transfer and I'm finished, right? So if in a case where the value of n, here the value of n of course is 100, but if I have a situation if n, right, if the value of n is going to be equal to 1, then what you're going to do is you're going to transfer, right? This is not a call on the functions, no recursion over here like the base case. You're going to transfer the top ring, right, which is the only ring you have available there, from tower from, right? You can go from tower from, in this case it's A, and you're going to go to tower 2, right, from tower 2. And when you finish, right, it's only one thing to move, then you're going to be returning, right? But in this case, that's not happening, right? I mean, the base, because you're starting with 100. So what you're going to do is, we say to move 100, the first thing you need to do is you want to move from tower A, from the from tower, right? From tower, there's a from tower A to tower C. That's going to be what? Right? You want to go from A to C. C, in this case, here's your C. This case, C started out as the extra tower, right? You want to go from the from tower to the extra tower. That leaves the third tower, the one that's neither from nor extra, that's the to tower. So that's going to be, in this case, that's going to be B. How many do you want to move from A to C? You want to move 99, right? In this case, it's n minus 1, right? Because n was 100, right? So in order to move 100 from the from tower to the to tower, you move 99 from the from tower to the extra tower, right? Now, after you do that, what's going to happen? Well, we saw, after you move the 99, we're going to end up with the 100 over here. And where is the 100 going to be? That's going to be in the from tower, right, tower A, and you're going to just transfer it over to B, as we saw. So after you've finished moving the 99, so step 3 is going to simply say transfer the top ring, of course it's the only one there because you moved them all away, from tower from to tower 2, right? And that's it. So then you'll have 100. The situation will be what? The situation will be 100 over here and 1 to 99 on tower C, right? So, and then what? So then you'll have the 100 over here, and then you want to move all those guys back. That's going to be the third step, right? In this case, we wrote that whole out. It's going to be the fourth step because we had the base case we looked at. So tower 4 is going to be move them back, right? And we're going to move them back by calling move again, because it's not a case of 1, right? We're going to call move again from where to where? We're going to go from the C tower, right? We go from the C tower to the B tower, and we're going to move, which is going to, and then we have the C tower. So the A is going to be the extra one, and we're going to move 99, right? So we're going to go from the extra tower, right, which was C in the beginning of this thing, to the 2 tower, and this is going to be which? This is going to be the from tower, and this is going to be n minus 1, right? And when we finish, we're going to have what we saw before. We're going to have, we'll have on tower A, we'll have no rings. On tower B, we'll have no rings. I mean, on tower C, we'll have no rings. And on tower B, we'll have moved everything from A to B, okay? So now let's actually work this thing through. Let's see what happens in the activation stack. And what we're going to do now, I'm going to do this now instead of A and B and so on. I'm going to move it. I'm going to do it more generally, and I'm going to say move from the from tower to the extra tower. Just make sure you understand this much at this point, and then we'll see the generalization right after this. But make sure this is clear. But before we do this, we're gonna look at the simulation. So I want to just make sure we understand what the activation record is going to look like over here. We're going to trace it for n is equal to 3, but let's see what the activation record looks like. So what is going to be in the activation record? So remember, what does the activation record have in general, right? It has all the local variables, right? I'm sorry, forget it has all the parameters, so what are the parameters? We have from, we have to, we have extra, we have n, right? So these are all the parameters. What else do we have? So if you have any local variables, because it has to really keep a snapshot. It has to keep a snapshot of what's going on. Remember, I gave you an analogy of imagine we're giving an exam, and we have only one copy of the exam, and that's being it's up there on the screen, and everyone can look at that. So you have only one copy of the program, but everybody has their own blue book, right? So every time the function is going to get called again and again and again by recursion, it's going to have its own copy of the activation record, right? And we'll see exactly how it grows and shrinks in a moment. So the question is, when for the algorithm to run, what information does it need? Well, it needs to know all the parameters from, to, extra, n. It needs local variables, but this doesn't have any local variables. And then when it returns, when I finish with one recursion, it's going to say return to where? So we saw we need a return pointer, right? We're going to need a return pointer. So that's that's the activation record looks like. And now let's take a look at the program as it runs. First, we're going to look again at what we just did up here, but a little bit more general terms, right? Instead of saying A, B, and C, we're going to talk about it in from, to, extra, and so on, and n minus 1. Basically, a repeat of this, but a little bit more general. We'll see a trace of half the algorithm, and watch the activation stack grow and shrink, and then. Okay, we're going to look at the towers of Hanoi problem we did in class. The basic idea was we've got these 3 towers, so we're going to call the towers A and B and C. And the idea is we start with n rings on tower A. So I have 1, 2, 3, and down to say n minus 1, and then n. And I want to get all those rings eventually from tower A to tower B. We want to do it recursively, and we saw that the basic idea is that first we're going to, in order to do that, we have to be able to free up that bottom ring, this one down here. So we have to somehow transfer these n minus 1 rings off of tower A, and we want to get them to tower C. So the algorithm is going to basically call the 3 towers the from tower. In this case, the from tower is A, and the 2 tower is going to be B. And the tower that's neither the from nor the to on any particular execution of the algorithm, we're going to call the extra tower, the one that's neither the from or the to. And we wrote the following pseudocode in class. We had a function called move. Here's the pseudocode called move. And move had the parameter which the tower from, the tower to, the tower extra, and n was the number of rings. And so the base case we saw, we did this in class, the base case was that if n is equal to 1, then there's no recursive call at all. So if n is equal to 1, then all we want to do is we said transfer the ring n from the from tower to the to tower and return. Right? That was the base case. So if we simply say go from A to B, move 1, they'll just be move that ring 1 and we're out of there. But let's say we have more than that. Say we want to move 100 rings. So then we have to move the first 99 from A to C. But in general terms, we want to move from the from tower to the extra one, right? In order to free it up so we can get the 100th one, the bottom one, to tower B. So then what we do is, the second step, if the base case is not true, is we're going to call this function move recursively. And we're going to say like this. We want to go from the front tower to the extra tower. And we want to, the third parameter is going to be the to tower. And we're going to be moving n minus 1. In this case, that's going to take the top n minus 1 and bring them from here to here. And the configuration will basically look like this, right? So we're going to have 1 to n over, we're going to have just n down here on the bottom, and will be here. And 1, 2, all the way up to n minus 1 will be here after call on step 2. At that point, we're ready to take this ring here and transfer it over. And that's not a call on the function move. Simply say transfer it. And we saw when we actually write the program, that'll be basically an output statement. We're going to say cout, as we saw in class. So step 3 is again a call to transfer the ring n from the from tower to the to tower. At that point, n will no longer be on tower A, which was the original from tower. That's going to be erased. It won't be here anymore. The tower still will. And n is going to be here. And we still have to move these guys back, right? The ones on this tower here. So we have to call move to bring these n minus 1 and put them on tower B. So that's another call on move. And we're going to say we're going to go from, this was originally this was the from tower, this was the to tower, this is the extra tower. So we're going to go from the extra tower to the to tower. So the third parameter is going to be the from tower. And we're going to be moving n minus 1. When we finish that, we're going to have a situation that basically has no rings on C and no rings on A, but we're going to have all the rings on tower B, and we're finished, and so therefore we say at this point, we say return. Okay, that's basically the idea. Now the question is, what happens when we run this program? We actually, of course, we have to run it by making a C++ program out of it, but if we try to simulate the algorithm, let's see what happens if we start with 3 rings over here, and we want to call the function move. We're going to call move, and we're going to say we're going to go from tower A to tower B. Tower C is going to be the extra tower, and we want to move 3. Let's check out the first couple of moves. Specifically, we want to see what happens on the activation stack when this algorithm executes. So the first question is, what does the activation stack look like? So we saw in class that the activation stack basically consists of all the formal parameters. In this case, we have from to extra n, so there are 4 parameters there. All local variables, well, there are no local variables in this function, plus the return point to return to, which point in the algorithm to return to after we finish executing a substep. So that means if we want to draw the activation stack, it basically looks something like this. The activation stack is going to have the following in it. It's going to have 1 slot for the from tower, another slot for the to tower, 1 slot for the extra, 1 slot for n, and it's going to have 1 slot for the return. In other words, what step do we go to when we return? So if we now execute this here, move, let's see what's going to happen. Let's actually try to work this thing out step by step. So the first thing that's going to happen is we're going to be calling move. So it's going to populate the activation stack, the activation record, and it's going to say I want to go from tower A, that's my from tower, to tower B. C is going to be the extra tower, and I want to move 3. And I'm going to call this from the main program. So when I return back, I'm going to basically be returning to wherever I was called for to the main. Okay, so when the recursion happens, the first thing that happens is the activation record gets populated, and then the program starts to execute. So now we come here in step 1. So it's going to now say essentially like this. By step 1, right, the first thing that happens is step 1. Let me get a different pen for a moment. Let's take a different color. Say something like this. So the first thing is now step 1. Step 1 says we're going to call move. This is what we did just now. We're going to call move for A, B, C, 3. Now, once we do that, we're going to come into this algorithm at step 1. But the first thing that's going to do is going to ask what the value of n is. Is n equal to 1? Well, currently the value of n is equal to 3, so that's going to be false. So now we're going to end up on step 2. Right? We start on step 1. We're going to end up on step 2 of the original call on move. What step 2 says is we're going to call move again, but this time we're going to go from the from tower, which is tower A, and the second parameter is going to be the current value of the extra tower. Well, the current value of the extra tower is C, right? So we're going to go from A to C. The 2 tower is going to be B, and n minus 1 is the parameter, so it's going to be 2. Those are the 4 parameters being passed in. And if you look at this, basically what it's telling it is that in order to accomplish the moving of 3 rings from A to B, what it's going to have to first do is move 2 rings from A to C, right? And so every call on the recursive function is going to result in a new record on the activation stack. So the activation record is going to look just like the other one. And we saw the recursive call is going to result first in populating the activation record and then going to do the algorithm. So this is going to say A, right? We just populate it with the parameters as they passed along. A, C, B. There's going to be 2. Now the question is, where do we return to? In other words, after we execute this particular call, where do we return to? Well, since we're calling from step 2 in the algorithm, when we come back, we're going to come to step 3, right? Just like in any program. So the return point is going to be to step 3. Okay, so we've populated the activation stack, and now we're ready to, the activation record, now we're ready to go into the program again. So we come into step 1 of the program, and again we ask, is n equal to 1? And the answer no, is n is not equal to 1. N is not equal to 1, n is equal to, the current value of n is 2. So what happens? We again call function move, right? So this is now by step 2, but by step 2 of what? Of the previous call of move ABC2. We're going to call move again. But what happens when we call move? We're going to have to populate the activation record. So the system creates a new activation record for us. And what's going to be called? So it says move of the from tower. What's the current from tower? It's going to be move of the current from tower. From tower, I just read it off of here, is A. And then the next one is the extra tower. The current extra tower is B. And the one that's neither A nor B is going to be the third one. So that's going to be that's T, which is C. And how many? It's n minus 1. Well, n is currently 2. N minus 1 is going to be 1. So it's going to make that call. It's going to call move A, B, C, 1. So this is going to be A. This is going to be B. That's going to be C. That's going to be 1. And what's the return point? Well, again, since we're calling from step 2, we're going to have to return to step 3. Okay, so we've populated the activation record. And now we are ready to, this thing should say 3, right? And now we're ready to execute the program. So we come in and we ask if n is equal to 1. Well, that's true. So this is going to be by step 1, right? By step 1 of this call, we're going to say, is n equal to 1? And in fact, yes, n is equal to 1. It's the n on top of the activation stack. So we're going to do a transfer, right? What everything in step 1 says, we're going to do a transfer of the ring n. In other words, of ring 1, that's the value of n, from the from tower to the to tower. Well, the from tower is tower A, and the to tower is tower B. So that's going to result in moving the ring 1 from the from tower to the to tower. It's going to put ring 1 over there, and of course, it's going to take ring 1 off of there. Right? So that's what happens. This is the first time that anything happened. And in fact, of course, anything can be moved only when it's on the top, and we see that happens right over here. Now, what happens after we do this transfer? We're going to transfer ring 1. We're going to transfer ring 1 from the tower from tower A to tower B, right? From tower A to tower B, and then what happens? And then return. Well, what happens when we return? What does return mean? Return means two things. Return means, number one, we're going to take the current top of the activation stack and we're going to pop it. We're going to get rid of it, and we're going to return to the previous level, right? We're going to turn to this previous level over here. This is going to be the new one over here, and we're going to return to step 3 of the previous level. So it's going to look like this. We're going to get rid of the top one here, just like that. This comes off, no longer here, and we're going to return to step 3 on the previous one. And that makes sense, right? We're going to be over here on step 3, right? Step 3, which makes sense. We just did step 2, and now we do step 3. What does step 3 say? Step 3 says transfer the ring n. So this is going to be, again, transfer ring n. What is ring n? It's the current value over here. This is ring n. So transfer ring 2 from where to where? From the from tower. My current from tower is A. And my to tower is C, so it's going to go from A to C. That's going to take this one here, and that's going to bring it from here and deposit it here. So when I do that, there's going to be a 2 here. The 2 is taken off of this. 2 is no longer going to be on there, and this system looks like this. 3 is going to be on A, 1 is going to be here, 2 is going to be here. Now what do I do after step 3? Well, after step 3, I go to step 4, right over here. And what does step 4 do? Right, notice it's this thing here. I've been indenting it appropriately. Step 4 says, let's do another call on move. And what's the call now? It says go from the extra tower to the to tower. Well, what's the extra tower? The extra tower is B, right? So we go from tower B to the to tower. The to tower is tower C. So I'm going to go from B to C, right? To move from B to C, from here, it's going to try to move to here. Which ring? And the from tower is going to be A. That's the third parameter. So B to C, and A is that. And how many am I moving? I'm moving n minus 1. Since the current value of n is 2, n minus 1 is going to be 1. And it's basically telling me to move ring 1 from the B to C. It's going to take this thing over here and basically move everything off so I can free it. Okay, I'm going to leave the rest as an exercise, but that's basically what happens as this program executes. So we saw the algorithm. We hopefully got the intuition about how that thing works. We saw what happens at the activation stack, and now the question is, so that was basically pseudocode. Can we turn this thing into a program? And the answer is, not only can we turn it into a program, it's really trivial. There's a very trivial translation from the pseudocode into the program. I'm going to work out a little bit for you, just show you how it might be done. And I'm going to leave it for you to try. I'm going to ask you actually to hand this in. It should not take you, once you understand this, it shouldn't take you more than 15 minutes on the outside. It's very, very straightforward. So let's see how this works. So the function is going to be called move, right? So we're going to write a function called move, right? That's the name of the function, called move. What's the function going to return? Well, the function is not going to return anything, right? It's not returning anything. It's going to tell you what to do at each step. It's going to, so let's see. So we're going to say it returns a void, right? Doesn't return anything. So we have a function, a void function. Let me just do it over here, a void function. And we're going to call the function move. And what are we going to pass in, right? The from tower, the to tower, the extra tower, and so on. So how are we going to represent these towers? Well, the simplest way to do this is to represent them as characters, right? Because what we're going to do is we're not going to actually print out pictures of these towers, of the rings moving through the towers, just we'll print out instructions, right? So when the program's going to say transfer some ring from tower this to tower that, it will actually just print out that instruction. So we're going to have 3 towers. So we're going to have a char for tower from, a char for tower 2, a char for tower extra, and then an integer for n, right? So from to extra, right? And then an integer for how many we're going to end up moving. So how do we translate line 1? So it's very simple. It's an if statement. So it's going to be if n is equal to 1. Then what do we want to do? So this has transfer. So we're going to simply say cout, and we're going to just write it out. We're going to say transfer, and just going to write it out. And so it says tower from. You're going to simply print the word tower and then whatever the value of f is. And then when it says tower 2, you're going to just print the word tower and then 2. And when it says return, so you're going to say return, right? So you're going to put this thing in brackets. There's going to be cout, and then after you do that, you're going to say return, right? So that's straightforward. How are you going to translate line 2? Line 2 is just a call on function move. So that is also just move, right? And now it's going to be just like you see here, from E, T, and -1. How do you translate line 3? Well, again, transfer, we're not going to actually move the rings. So again, it's going to be, you're going to print out what you want the program to do, or person following these instructions. So it's going to transfer top ring. Well, where's the top ring on tower from, right? So you'd say transfer, and then you'd say ring, right? And then which ring? It's whatever's on top of tower from, right? So you would say top ring from tower from, and it becomes an output statement. What about number 4? So again, it's a call on move, right? And what about return? It's simply you close it up and it automatically returns. So obviously you see I didn't write the whole thing. I want you to do this translation. It's not difficult. It's really not difficult. It's very straightforward translation, and make sure you can get it to run. So what's the main program going to look like? What will the main look like? So the main is going to be simply a call on this. You're going to call move, and then you're going to have the various parameters and n, whatever n is going to be, right? So whatever it's going to be, if you want to do it for 7, you do for 7, right? Or you might even ask the user, give me a value for how many, well, what does n represent, right? There's always 3 rings, so n is going to be, there's always 3 towers, so n is going to be the number of rings. So you'd say to the user, say, please give me the number of rings, and it should work. Please try it. Make sure you really understand how this thing works. And again, I just want to repeat what I said earlier. You have to think of recursion on a high level. You can't think of what's going on in the the runtime stack. That said, what we did in the simulation of the runtime stack is the first half, right? We managed to move tower 1 and ring 1 and 2 to tower C, and then we move the number 3 over. I want you to just do the rest of it. Just play computer and watch how it works to bring the rest over. Another tower 1, ring 1 and 2 back onto tower B, and the whole thing works. Hopefully when you do this, you get a stronger feel for how the whole process works. Now, what I want to do now before we finish up here is to see if we can get a feel for how many moves does the algorithm actually take. So let's see. If n is equal to 1, right? N is the number of rings. So if n is 1, and we want to go, here's tower A, and here's tower B, and here's tower C, right? So if there's only 1 ring, so how many moves does it take? Well, you just bring this over, right? So it takes 1 ring. It takes 1 move. What about if I have 2 rings? How does that work? So if I have 2 rings, right? I have ring 1 and 2. So remember, the whole point is that we have to make sure that we get this free. We have to get ring 1 off of it. So if I have 2 rings, right? So the first thing I have to do is free it up. So, and I have to end up with 1 and 2 over here. So I have to get 1 off. Where should I put 1? I have to put 1 over here, and then I move 2 over here, and then I move 1 back over here, right? So if I have 2 rings, it's going to be 3 moves. If I have 3 rings, we saw it's going to take 7 moves. What about if I have 4 rings? So if I have 4 rings, let's see if we can figure this thing out. So tower A and tower B and tower C. So I have 4 rings, 1, 2, 3, 4. Now again, the basic idea is to free up ring number 4. So I have to get 1, 2, and 3 here, right? So what we saw earlier is that it doesn't make a difference in terms of the number of moves. It doesn't make a difference. I'm moving from tower A to tower B or tower A to tower C. The number of moves is the same. So the first phase of it is that I have to get these 3 rings, 1, 2, and 3, up to tower C. Well, that I know, right? That's 3 rings. That I know already is going to take me 7 moves. So 7 moves is going to end up with a situation that looks like this, right? 1, 2, 3 end up on C. Then I have to get 4 to move that over. So how many moves is that? Well, 4 is going to end up here. So that is 1 move, right? So that's 1 move. But to finish it up, I need everything on tower B. So the third step is going to be to move 1, 2, and 3 back to here. Now, it doesn't make a difference that there's a 4 on the bottom, because that's not going to interfere with anything, because 1, 2, and 3 are smaller than 4, right? And there's nothing over here. So that's also going to be 7 moves. So it's going to be 7 moves to get them from A to B, 1 move to bring the 4 over, and another 7 moves to bring them back. So that's going to be 15 moves. The same exact thinking is if I have 5, right? If I have 5, then what? If I start with 5 over here, so I have 1, 2, 3, 4, 5. I've got to get 1, 2, 3, 4 rings onto tower C, right? Again, tower A, B, and C. Well, I know how much that costs. That's 15 moves. Then 1 move to bring 5 over, and then another 15 moves to bring the 1, 2, 3, 4 from C back to B. So it's another 15 moves. And so that's going to be a total of 31 moves. So the pattern should be clear. The pattern should be clear. So basically, what about 6? Well, let's see. How did I get 3? How did I get 3? Let's look at this. How did I get this one over here? 7. So I have to do twice the one before plus 1, right? Because this means I have rings 1, 2, and 3. I have to move 1 and 2 over. That takes 3 moves. That's the one right on top of me. Then move it over 1, and then move them back. So it's 2 times the previous one plus 1. Same thing with this 15, right? In order to move 4 rings, I have to move 3 rings twice. Once to free it up and once to get them back on B. So it's 2 times 7 plus 1. Same with 31. I have to move 4 rings twice plus 1, right, where I do the move of ring 5 from A to B. And so this is going to be what? This is going to be 2 times 31, which is 62, plus 1, which is 63, and so on down the line. So I can actually write a function, and if, let's say, Han of n is the number of moves I have to make to move n rings. So let's see how that works. We can write a simple recursion. It's going to be 1 if n is equal to 1, right? If n is equal to 1, it's 1, right, for n equal to 1. But if n is not equal to 1, right, so how many moves do I move, let's say, for n greater than 1? Well, it's going to be Han, remember, Han of n minus 1. Han of n minus 1 is the number to move n minus 1 rings. Like if n is equal to 4, Han of n minus 1 is 7. right? But it's going to be twice that, right? Because once on the way in and once on the way out. So it's going to be 2 times Han of n plus 1 to move the other one. Okay, so that's a recursive formula for figuring this out. But if you think about it also a little bit, I can sort of guess at what the formula would be. So if you look at, let's say, when n is equal to 1, let's look at his power. These look like close to powers of 2, right? So for n is equal to 1, here's n. Let's see if we can figure this out now. So here is n, and here is Han of n. So if n is equal to, this is going to be the number of moves, right? Number of moves is what we called Han of n, right? So if n is equal to 1, then it's 1 move. That looks like 2 to the 0. When n is equal to 2, it's 3 moves. That looks like 2 squared minus 1. So instead of writing 2 to the 0, I can sort of write it as 2 to the 1 minus 1. When n is equal to 3, then what is it? It's 1 less than 2 to the 3rd. So it's 2 to the 3rd minus 1. And this thing goes all the way down. So what is 2 to the 5? It's 32 minus 1. So in general, for the case of n, it's going to be 2 to the n minus 1. So I have a general idea here that this recursive function, right, this thing Han of n, is really equal to 2 to the n minus 1. So this is called, this over here that we have, that's a recursive definition. And this thing is called the closed form of that. By the closed form, we mean there is no recursion involved. It's directly some function of n. Okay, so here we have an algorithm for solving, a recursive algorithm for solving the towers of Hanoi. And then we have a function that tells us how many moves it actually takes for n. And lo and behold, it is exponential, right? The number of moves is exponential. Now, a question you might want to think about before we finish this thing up is that, is there any faster algorithm, right? In other words, if I'm clever enough, so we have this recursion, the recursion was exponential, right? We looked at the Fibonacci. So when we did the Fibonacci one way, namely by using recursion, we ended up with an exponential number of steps, right? Remember, something like on the order of, it was bounded by 2 to the n over 2, right? As n got bigger and bigger. That's exponential. But then we saw, when we looked at a bottom-up approach to that, we ended up just filling up a table. It was basically n steps. So what about this case over here? What about the case of the towers of Hanoi? Is there any way that I can do it in less than 2 to the n steps? Think about that. Is there any way to do less than 2 to the n steps? Right? This is one of the problems we talked about at the very beginning of the semester. Certain things, in terms of the complexity of computation, are inherent. Like we saw that if I ask you to print out all the subsets of a set of n elements, well, how many subsets? We saw there are 2 to the n subsets. So if you're going to print them all out, just the printing itself is going to take 2 to the n steps. So it's intrinsic to the problem itself that you can't do it any faster, right? You can't do it with less steps than 2 to the n. But on the other hand, we just saw with Fibonacci that one approach, namely when we use recursion, that leads to an exponential amount of work. But if we do it sequentially, bottom up, it's linear, right? It just end up filling in the table. So what about this one? So I claim that this is intrinsically exponential, and see if you can figure out why that would be.